Now we're to the last bit of material that we're going to cover in this trigonometry class. So we still have two more sections left, section 7.4 and 7.5, but they're both about something called vectors. So the thing about vectors is that this is actually a topic that you might see sooner than some of the other ones that we've looked at in chapter 7. So vectors is a really important topic specifically in physics. So it's possible that if you're in a physics class right now, you might have already started to talk about vectors. So what we're going to look at in these sections is really to see how vectors relates back to a lot of what we've talked about in trigonometry already. So on this first page, we have a lot of definitions that go along with vectors. The thing about vectors is that we're trying to indicate both a direction of something and a magnitude of something. And so for that reason, one thing with vectors is it's not just a line that we're looking at, but it's a line with an arrow. It's a line with an arrow. It's a line with an arrow, and that's because we're trying to indicate a direction. So here's some terms we have. So scalar is basically just a number. Like most of the numbers that we've been dealing with so far, we could probably call them scalars. A vector, though, is that we're looking at two values together. And so that's the magnitude, and also we're indicating direction at the same time. So with a vector, it's an arrow. With a vector, it's an arrow where we have an initial point. That's where you start. Like for the arrow I drew up there, that would be our initial point, and something called terminal point, which is where it ends. So terminal point for this vector would be where we have that arrowhead. Magnitude is indicating the strength, but that's basically the length of the line. So what we've looked at so far, we could think about synonyms as being hypotenuse, radius, absolute value, modulus. It's all indicating the length, which is the strength of the vector. Displacement has to do with the change in position. Vector equality, the idea of vector equality is that if I have a vector, let's say I'm going to try something simple like this, starts at 0, 0, and it ends at 2, 2, that vector is actually equal to this vector over here. And that's because it doesn't matter that their starting points are different. It matters that their length is the same and their direction is the same. And so I could even put some more vectors on here that I would call equal vectors. And so for vector notation, there's actually two notations that we're going to talk about. And so one of the notations that we're going to use for vectors is this form where it basically looks like an ordered pair. It's not, but it has those angle-looking notation on either side. And so what this is telling us is the A is telling us the change of the X value, and the B is telling us the change in the Y value. We could write vectors also in this notation, where A and B represent the same thing. A is the change of X, B is the change of Y, but we use this IJ notation. So one thing that's really important to mention here is this I does not represent an imaginary number. It's a different notation, where here I is just indicating the direction change to the left or right, and J is indicating the direction change up or down. Last thing to mention notation-wise is that when we write a vector, typically we write it as a letter that's bold-faced to indicate that we are talking about a vector. Let's start with this example. So here we have a vector v where it has an initial point, -5, -2, and a terminal point at 3, 4. So I could go ahead and graph this vector. So let's first find the initial point. Let me put a point there. And the terminal point, 3, 4, would be right here. And so I would want to draw the arrow starting from the initial point and ending at the terminal point. So this is a graph of the vector v. Find the magnitude. So in order to find the magnitude, we need to see the change of x and the change of y. So the change of x is like what we're doing is really trying to draw a triangle around here. Similar to if we had, let's say, a linear equation and we were trying to find the slope looking at rise over run. Really, it's the same process here. So how are the x's changing? That's our a value. And how are the b's changing? That's, how are the y's changing? That's the b value. We could figure this out by looking at the ordered pairs. So let me write them down. So in this case, a would be the change of x, so we could indicate that as 3 minus -5, which is 8. So it's saying this distance here, it's kind of in green. We could count it, and it ends up being 8. And do the same thing for b. And we get a b value of 6. To figure out the magnitude, we can use the Pythagorean theorem. Here we've got 8, square root of 8 squared plus 6 squared. So we have that the magnitude is equal to 10. And that's the distance right here. Now let's write it using the two different kinds of vector notation. The first one is called component form. So I've already done the work to find a and b, so it's just writing it in that form. So it's 8, 6 is one way that we could write vector v. And we can write it in the other form as well. So vector v could also be rewritten as 8i plus 6j. Now let's look at vector arithmetic. So we're going to specifically look at adding and subtracting vectors and multiplying by a scalar. So I'm going to go ahead and draw these as well. So let me go ahead and draw each vector. So you'll notice that I'm just given it in vector form, and so I actually don't know what the initial point is or the terminal point, but I could draw these anywhere. So I'm going to start by drawing the first one just at a starting point of 0, 0. So let's see, if I start at 0, 0, 5i minus 3j would be 5, -3 right down here. This is our vector v. So the first thing that we're trying to do is add vector v plus vector w. So what does this mean sort of graphically speaking? It actually means like if we had drawn vector v like we did, then we use that terminal point to start the next one, and we draw vector w. So let me go ahead and draw vector w starting from where vector v ended. So in that case, it means the x value would move over 2, and the y value would move up 4, which would be right here. So this is, graphically speaking, what happens when we do v plus w. Now let's actually show this algebraically as well. So let me write vector v. So 5i minus 3j plus 2i plus 4j. It basically follows the rules of like terms. I can combine the i's together. So that's going to be 7i. And I can combine the j's together. So -3j plus 4j is plus j or plus 1j. I'm just going to write it like that. So this is the answer. But if we go ahead and look at our graph, if we drew a vector from the original starting point, which was 0, 0, and connected it to where those ended, that is actually the vector v plus w. And you can see that it ends right at that same point that we had just found. 7, 1. And so if we started at 0, 0, that vector would be written as 7i plus j. And now let's look at subtraction. So subtraction for this one, let me do the algebraic part first. So that would be 5i minus 3j minus w, 2i plus 4j. With subtraction, we always want to be careful because it's easy to forget to distribute that negative. So before I would combine like terms, I would distribute that negative. So it's 5i minus 3j minus 2i minus 4j. So the final answer, combining like terms, would be 3i minus 7j. So that's the vector we get when we subtract w from v. So what does that look like on the graph? If we have a negative vector, it means it moves in the opposite direction. So it's like you take the vector and you would move or rotate 180 degrees. So let's say I started with vector v. I'm not going to change that, because in either case, we're starting with vector v. I'm going to start it at 0, 0 because I can use any point as the initial point. So what does it mean to subtract vector w? So I have vector w written here, but negative, what does negative w look like? Well, I could actually rewrite that. Instead of 2i plus 4j, negative w is actually negative 2i minus 4j. So if I try to graph that at the end of my vector v, that would mean my x's would move left 2, and then my y's would move down 4. 2, 3, 4, and it would end right here. And so if you see, graphically what's happening is that it looks just like it's a mirror image of a w. And that's because if we go backwards, it's kind of like rotating 180 degrees. So the final answer, though, would be starting at 0, 0 and ending right there. And right there happens to be the point, if we look here, 3, negative 7, which is exactly the answer we got when we did it algebraically. So 3i plus 7j. The last thing we're doing is something called scalar multiplication. So scalar multiplication is that v is the vector, and we're not multiplying it by another vector because that's something different, and we're actually going to look at that in section 7.5. Scalar multiplication is just multiplying by a single number, not a vector. And so if we do this algebraically, it would be just like distributing the 2. So 2 times, if I rewrite vector v, that's 5i minus 3j. I can just distribute that. So that becomes 10i minus 6j. And that's our final answer. So what does that mean graphically speaking? Well, if we're multiplying it by 2, we're doubling it. So if we look at our original vector v, and so it doesn't get too messy on our graph here, I'm going to erase the work that we've already done. And if I wanted to do 2 times v, I would multiply by another one. So I'm just going to put another v right at the end of this one. So I would go to the right 5. 1, 2, 3, 4, 5. And down 3. 1, 2, 3. And you'll see that where we end is 10, negative 6. And the reason that works the way it does is really because 2v is the same thing as not v plus w, v plus v. Just like 3v would mean v plus v plus v. Now let's look at more vector arithmetic where we put it all together in the same problem, and for this one I'm not going to graph it. But I am going to color code this here. This is what we're trying to figure out here. 5 times v plus 2w minus s. So I'm going to plug in what v is right here. And notice here we're looking at a component form. W I'm going to plug in right here. And s, I'm going to plug it in right here. And so let me rewrite what we're looking for. So it's 5 times v, which is 6 negative 10, plus 2 times w, which is negative 2, 8, minus s, which is negative 3, negative 1. So really when we're solving this problem, we're going to use algebra, and we want to follow the same order of operations rules that we would use for algebra. So for this one, I might go ahead and first distribute this 2 because that's multiplication there. So that would be 5. I'm not doing anything with this first vector. Plus, now this is going to become negative 4, 16. And I haven't done anything with the vector s either, so I've left that one alone. The next thing I want to go ahead and do is to add these two vectors together, which is really adding the a components together first and then adding the b components together. So that's going to be 6 plus negative 4, which is going to give us 2, and then negative 10 plus 16, which is going to be 6. So that becomes 5 times the vector 2, 6, minus s, which we haven't done anything with vector s yet. Okay, so now at this point, before I would subtract vector s, I want to do another distribution here because we've got scalar multiplication. So let me go ahead and multiply each piece by 5. So now that vector becomes 10, 30, and then subtracting vector s. So the last step is to do the subtraction. And so you might want to, before you actually do that, change it to addition and change the sign over here, because just like with any subtraction, it's really easy to forget to distribute it to the second part. And so this is the same thing as saying 1030 plus 31. So the final answer is going to be 13, 31. And that's our final answer, which is another vector. With these last couple of examples, what we're going to look at are some types of applications. There's tons of applications with vectors. We're just going to look at a couple here. So the first one says, a kickboxer kicks a bag at an angle of 45 degrees from the horizontal with a force of 250 newtons. Write the force vector F in terms of I and J. So when it says writing it in terms of I of J, that means our final answer is going to be something like AI BJ. And what we need to find then is A and B. So if we try to kind of visualize what's happening, let's start at the origin 0, 0. So our vector, if the bag, the kick bag is getting kicked at an angle of 45 degrees, I'm actually just trying to draw an approximation, so kind of don't pay attention to these numbers just now. But this angle right in here would be 45 degrees. And the 250 newtons is saying that's the magnitude. So that's the force that's getting exerted at that 45 degree angle. A is equal to r cosine theta and b is equal to r sine of theta. So putting this all together, we get that the vector f is equal to 250, because that's our magnitude or r value, cosine of 45 degrees, and then I'll put the I, plus 250 sine of 45 degrees, that's our b, and then the j. So simplifying here, 45 degrees, if we draw the 45, 45, 90 triangle, we have 1, 1, square root of 2. So that means both sine and cosine are 1 over square root of 2, which could be rewritten as square root of 2 over 2 if we rationalize the denominator. So that becomes 250 times square root of 2 over 2i plus 250 square root of 2 over 2j. Simplifying a little bit more, we get 125 square root of 2i plus 125 square root of 2j. So if we want the exact answer for the vector, this would be the exact answer for the vector. If we wanted to get an approximation, we could plug 125 times square root of 2 into the calculator to get an approximation, and that would be about 176.8. So it would be 176.8i plus 176.8j. Let's look at one more application. So for this example, it says a plane travels north 30 degrees west at 450 miles per hour and encounters a wind blowing due west at 30 miles per hour. So first I want to draw each one as a vector. So this first one dealing with the plane, we're going to be using bearing here. And so to recall, what does that mean? Well, north 30 degrees west, if we think about north, south, east, and west here, that means we start in the north direction, and that from that we're going to rotate 30 degrees in the western direction. So that would be rotating 30 degrees here, which would end up with a line about here. I'm sort of approximating at this point. So this is the airplane that I'm trying to draw right now, the vector for the airplane. So it's traveling north 30 degrees west at 450 miles per hour. So the 450 is going to be the magnitude. And if we want to look at the angle, the thing is that we've gotten this based on the bearing, but that's not really how we use angles when we draw them in trig. So I want to convert this to what we have done in trig, which is that we use reference angles, but they need to be based off of the x-axis. So that means what I want to figure out is this angle right here. So since this quadrant is 90 degrees here, we could say that it's 90 degrees minus the 30. So it's 60 degrees. And we could draw that special triangle. So let's say if this is our airplane triangle here, if it's 60 degrees is the degrees that we're working with. I know that the magnitude is 450. And for now I'm going to erase this 450 because I'm just writing our regular special triangle for 30, 60, 90 degrees here. So I have 1, and I should make it a -1, square root of 3, and 2. So first we want to express the velocity of the plane as a component vector. So if we do something similar to what we did in the last example, but in this case we're doing component vector instead of I and j form, remember that the a value or the x value is the same thing as the magnitude, which in this case is 450 times cosine of our angle, theta, and our b value is going to be 450 times sine of theta. And the thing is, if I write it this way, that's what allows me to convert it to that special triangle of like 1 square root of 3, 2, because I'm multiplying by 450 at the end to recognize that the hypotenuse is not actually 2. It's going to be 450 because that's what the magnitude is. So then if we just keep solving here, it's going to be 450, and then cosine of that angle is going to be negative 1 over 2. And sine of that is going to be 450 times square root of 3 over 2. So our vector VP, and then I'm going to simplify it as well, like 450 divided by 2. Which is going to be negative 225, comma, positive 225 square root of 3. And I'll plug that into the calculator too to get the approximation. I'll round this to, how about, I round this to 389.7. So this vector is for the airplane. We also want to write a vector for the velocity of the wind. So the wind is blowing due west at 30 miles per hour. So I'm going to just draw another diagram down here just so my diagram I have doesn't get too crowded. So north, west, east, south. So if the wind is going due west at 30 miles an hour, that means my vector is just going to be going right across this X line right here. And so if we wanted to express that as a vector, we could express it as negative 30, 0. And that's because the 0 is indicating it's not moving up or down, it's going directly west. So the X direction would be negative 30. Now we want to figure out something called the true velocity of the plane as a vector component, a component vector. So basically what this means, we're going to do some vector arithmetic. So the vector arithmetic is going to be that the true velocity is equal to the velocity of the plane plus the velocity of the wind. And if I did add that to my diagram, it's like if we had added an extra vector here because of the 30 miles per hour due west, what that means is that the actual plane, now my diagram's getting crowded here, is something like this, where it's not quite moving at that north 30 degrees west because the wind is pulling it a little bit more in the west direction. So we can figure that out by doing vector arithmetic. And I'm going to use our approximate value here. So we take the plane vector plus the wind vector, which equals negative 255, 389.7. This would be the true vector, the true velocity of the plane written as a vector. And so on that diagram, it's that blue, it's the vector that's in blue. What about the true speed of the plane? This really means that we need the magnitude of that blue line is the square root of 255 squared plus 389.7 squared. And if we plug that into the calculator, we should get an approximate value here of about 465.1 miles per hour. So basically that's telling us that with the wind that's moving to the west, it's actually helping the airplane move a little bit faster than that 450 miles per hour. And now let's work backwards to find, well, what is the true bearing, which means we need to figure out the angle. Since we know our A and B values, what we're going to use is the tangent. So tangent of the angle theta is equal to our y value, which is the 389.7 over negative 255. And honestly, I'm actually just going to plug it in as positive because I just want the reference angle anyways. And then I can use the inverse button. Tangent inverse of all of that is going to give us our reference angle. And so I'm going to plug this into the calculator. And that gives me about 56.8 degrees. And it's important to know that what we found is the reference angle. It's not actually the angle that we need for this problem. Our original reference angle was 60 degrees. And so now our reference angle is 56.8 degrees, which means that that angle is a little smaller, which makes sense because the wind is pushing it out to the west. So it makes sense that that angle would be smaller. Now I just need to convert this to bearing, which is going backwards from what I did before. So I need, and I feel like I need to draw a diagram here. So let me erase this one here to kind of talk about what's happening. So we have, once we did our addition of vectors here, we found this to be our reference angle, 56.8 degrees. In order to write it as a bearing, we need this value. I'm going to call this beta, this angle right here. So to do that, I can do, or to find it, I could do 90 minus 56.8, which is 33.2 degrees. So then to convert this to bearing would be north 33.2 degrees west. And that's the final answer for this one.